Hello boys and girls. My name is Stephen Hawking, and today I am going to teach you some physics.
Soccer is an Olympic sport that includes a lot of physics. It includes projectile motion, Newton's laws, and even has unwanted forces that we're trying to get rid of using various technologies. Let's go check out what Ian's doing. Ian, what are you doing?
Just polishing my soccer ball for the big game next week.
Oh, okay.
It's got to be nice and shiny so all the ladies like it.
Big I.
Special K.
Background information.
You know what it is.
Here we go.
The force of gravity. The force that's always acting on an object on Earth. That causes the accelerate at an object at 9.8 meters per second toward the center of the Earth.
Force of kinetic friction. The force acts in the opposite direction of the object. Can be calculated by Fk equals Fn times Uk.
You're probably wondering what UK is. Well, I'm gonna tell ya. UK is the coefficient of kinetic friction. You know it's got no units, son.
Yo, F normal is the force perpendicular to the surface when the object is on. Counteracts the y component of the force of gravity, Ian Lee.
The applied force. It's the force that you apply. Like a push or a pull.
Yeah. Projectile motion is the motion of an object that has been projected into the air horizontally or at an angle. When in the air, there is only one force acting on the object, which is gravity.
You know we're talking about Newton's 3 laws? First law, an object in motion wants to stay in motion, and an object at rest wants to stay at rest.
Second law, an object will accelerate in the direction of the net force net equals ma.
Third law, last one. For every action, there's an equal or opposite reaction.
Here we go. Acceleration is the rate at which an object increases its velocity or does the opposite and decreases its velocity.
Net force. The last one. We're almost done. The difference forces acting in opposite directions on an object. What?
Big I, special K out.
Special K. Yeah.
In the early 1900s to 1950s, soccer balls were made out of a leather, and this leather was very heavy and got even heavier in the rain. When it rained, these balls absorbed the water and they'd get even heavier, which made it very hurtful towards the head if you try to hit it. But nowadays they have developed a new material for the balls using ethylene vinyl acetate and thermoplastic polyurethanes to make the ball around 420 to 445 grams and have less than 10% absorption rate of water. This very lightness of the ball, light mass, helps the acceleration of the ball go very much faster because of Newton's second law, which states F net equals mass times acceleration, which would then become F net divided by mass equal acceleration, which shows that the smaller the mass is, the more acceleration there will be on the ball.
When a player in soccer is heading the ball, Newton's third law comes into play. As the ball approaches the player with an applied force, the ball will bounce off the player's head with a reaction force equal and opposite to the applied force that the ball approached the player with. Now, if the ball was to approach much faster than what was just shown, then the ball will travel much further due to the increased reaction force.
Nowadays we know that a soccer ball is round, but that's the obvious choice. But what could they have been experimenting with back in the day when they were trying to find the most aerodynamic thing? Maybe a puck? Nope. That didn't work very well. Maybe a baseball? Nope. That's too hard. Right shape this time. And then the soccer ball. That makes so... Look at that. It goes so far. It's the right mass. Wow. That just makes sense. Look at that aerodynamics. In soccer, you want the player's effort to keep the ball moving as minimal as possible. So that would require there to be a very low kinetic friction. Why don't we try the puck? Not very far. The baseball? Not very far either. What about the soccer ball? Whoa! Look at that! Almost double the length. Way to go, Kyle.
Soccer cleat's aerodynamic shape allows it to move faster through the air, which increases the net force that a player can apply onto the ball in a game of soccer. As this net force is increased, this also increases the acceleration of the ball, as stated by Newton's second law. Ian, let's test this theory. Kick the ball with the cleat first. As you can see, that went pretty far. Let's see what happens when he kicks it with his normal shoe. The ball didn't even go close to as far. Newton's third law states that every action force has a reaction force. So when Ian kicks the ball, there's a reaction force coming back at his foot. But due to his cleat absorbing some of that reaction force, his foot is not hurt by the ball being kicked. Hey Ian, pass the ball. Ah! Kinda hurt my foot, but it doesn't hurt Ian's at all.
When Kyle is wearing lots of clothes, and clothes that have more mass to them, there's a greater force of gravity acting on him, which would cause his legs to tire faster because there's more force acting on his body, which would make him more tired by the end of the game and by the end of a long season. Now, with his less mass on in his spiffy soccer jersey, now that his mass is less, according to Newton's second law, he'll have a greater acceleration. Whoa! With the low kinetic friction between Kyle's skin and his shirt, the material in the shirt will cause there to be a lower kinetic friction, which will cause him to be more comfortable during the game and let him focus on the game and not how he feels in his shirt. He'll pretty much feel naked.
When a soccer player falls on an artificial turf field, there's an applied force of them hitting the ground along with a reaction force coming back at them, which then can injure the player. But when a player hits an artificial turf field with rubber beads in it, these rubber beads absorb some of the applied force impact, thus lowering the reaction force. So let's see what happens when Ian falls down.
I got the ball!
Did that hurt, Ian?
I bounced right back up.
Well, there you go.
Great.
Look at that. And that's how an artificial turf field works.
In soccer, when you have a free kick, the wall has to stand 10 meters away from the player taking the kick. So I know that Kyle's 10 meters away from me, and I know that Kyle's 2 meters tall. So, if I know that I can kick the ball 15 meters per second, 45 degrees above the horizontal every time, how do I know if I'm going to get it over Kyle's head, maybe even into the goal? For right now, I'm just planning on trying to get over Kyle's head. So I'm just going to take a timeout from the game here and just do a couple.
What is he doing? Calculations.
Okay, I think it might work. This could be interesting though. The calculations that Ian did while taking the kick to find out whether he could get over Kyle were calculations for any regular projectile motion equation. He knew that Kyle was 10 meters away from him and that Kyle's 2 meters tall and that he was kicking the ball at a 45-degree angle 15 meters per second. He first figured out what the time would be in the x direction at 10 meters. So he got his v1 in the x, his direction, his displacement, didn't know the time, and he used the equation v equals d over t, and found the time would be 0.943 seconds at 10 meters in the y, in the x. Then, in the y direction, he used this equation, this kinematics equation, with these variables to find out how high the ball would be at 10 meters. And he found the ball would be 5.64 meters in the air, making it well over Kyle's head. But what Ian didn't find out during the game, because he was so pressured, he didn't have time, he didn't realize that the net, which was 20 meters away and 2.44 meters tall, was a whole nother challenge. He multiplied the time for the x in part 1 by 2 because he knows that it was double the distance, and since there's no acceleration in x, he didn't have to use a whole nother equation. Use the same equation in the y direction. Don't know what displacement is. v1 in the y, time, and his acceleration. Use the same equation as before, and we found out that the ball would be 2.57 meters in the air, making it soaring over the net by 0.13 meters. Ian misses the goal even though he made it over Kyle's head with the kick. Maybe next time, kid.
In soccer, projectile motion is also seen when someone is doing a throw-in. This is because the only force acting on the ball while it's in the air is gravity, while you're neglecting air resistance.